There's something hiding in the heart of our own galaxy, lurking in the dark. It packs the mass of 4.3 million suns, and its gravitational pull is so powerful it holds the entire Milky Way together. For decades, scientists chased this ghost, an invisible anchor they could feel but could never see. They knew it was there, but it would take 50 years, a telescope the size of our planet, and a Nobel Prize-winning breakthrough to finally hunt it down and reveal the monster at our galaxy's core. This isn't just a story about finding one thing. It's about a multi-generational quest that broke the known limits of technology and our understanding of the universe itself. It's a detective story written in the language of radio waves and starlight, a tale of chasing shadows across 27,000 light years. So how did we find it? How did we prove what it was? And what did we see when we finally stared it in the eye? To get how we got here, to the first ever image of the behemoth in our galactic backyard, we need to go back in time, back to a quiet field in New Jersey, and an accidental discovery that would change astronomy forever. Our story starts not with a telescope aimed at the stars, but with a strange antenna pointed at the horizon. The year is 1931, and a young engineer at Bell Telephone Laboratories, Karl Jansky, has a weird assignment. His employer is trying to launch a new transatlantic radio telephone service, but there's a problem. A persistent, faint hiss of static is messing with the signal. Jansky's job? Find out where the noise is coming from. To do this, he built a wild-looking contraption in a field in Holmdel, New Jersey. It was a massive, rotating antenna, 100 feet long, built on a set of wheels from a Ford Model T. It looked more like some kind of abstract farm equipment, and his co-workers appropriately nicknamed it Jansky's merry-go-round. For months, he carefully tracked the static. Two sources were easy to identify: nearby thunderstorms and distant thunderstorms. But there was a third hiss he just couldn't place. It was faint but steady, and as he rotated his antenna, he noticed something strange. At first, he thought the sun was the culprit. But as the days turned into weeks, he realized the signal didn't repeat every 24 hours. It was on a cycle of 23 hours and 56 minutes. Any astronomer will tell you that number is a dead giveaway. That isn't a solar day, it's a sidereal day, the time it takes Earth to rotate relative to the distant, fixed stars. This was the smoking gun. The noise wasn't coming from Earth, or even our solar system. It was coming from deep space. By 1933, he'd pinpointed its origin. The hiss was loudest when his antenna was pointing toward the constellation of Sagittarius, a region astronomers already suspected was the center of our Milky Way. Karl Jansky had, completely by accident, become the first person to ever detect radio waves from the cosmos. He had just invented an entire field, radio astronomy. His discovery made headlines, even landing on the front page of the New York Times in May 1933. But in the middle of the Great Depression, the scientific community barely reacted. Bell Labs, having learned the static was from outer space and thus unremovable, lost interest and reassigned Jansky. He had opened a brand new window onto the universe. But for more than a decade, almost nobody looked through it. The trail went cold. It wasn't until after World War II that radio astronomy really took off. Technology developed during the war, like radar and sensitive radio receivers, was suddenly available to scientists. All over the world, astronomers started building huge radio dishes to map this newly visible universe. And as their instruments got better, they kept coming back to that powerful, unexplained signal from Sagittarius. By the early 1970s, the tech had taken a huge leap forward. Instead of single dishes, astronomers were now using arrays of telescopes linked together, a technique called interferometry. By combining signals from multiple antennas, they could create a virtual telescope with incredible resolving power, letting them see much finer details. In February 1974, two young radio astronomers, Bruce Ballack and Robert L. Brown, were using the National Radio Astronomy Observatory's interferometer. They aimed their array right at the galactic center, a region known as Sagittarius A, and they saw something no one had seen before. Past observations showed a big fuzzy cloud of radio waves, but with their sharper vision, Ballack and Brown saw a tiny, incredibly bright point of light embedded within it. It was a compact radio source, and its light wasn't coming from heat like a star. It was being generated by some other high-energy process, probably electrons spiraling in a strong magnetic field. They knew they'd found the precise energetic heart of the Milky Way. They published their discovery in December 1974. The ghost finally had an address, but it didn't have its famous name yet. That came in 1982 when Robert L. Brown decided it needed a special name to set it apart from the larger Sagittarius A region. Thinking back to his studies in atomic physics, he remembered how excited states of atoms are marked with an asterisk. This was the most exciting thing at the center of the galaxy, so he called it Sagittarius A star. The name stuck. But the biggest question of all remained. What was it? The intense radio waves pointed to something incredibly powerful. Was it a super-dense cluster of stars, tearing each other apart, the remains of a gigantic supernova? Or was it something far weirder, an idea that came from Einstein's theory of general relativity but was still seen as a mathematical fantasy? Could it be a black hole? Back then, the idea of a supermassive black hole lurking at the center of a galaxy was still pretty fringe. The evidence for Sagittarius A star was strong, but it was all indirect. It was like hearing a lion roar in the jungle at night. You know something big is out there, but you have no idea what it really is. To find out, astronomers had to do more than just listen. They had to watch. They needed to see how this invisible giant was pulling the strings. The hunt was about to heat up. To prove a black hole exists, you have to do two things. First, show there's a ridiculous amount of mass crammed into a tiny space. Second, rule out literally everything else. This was the challenge for astronomers in the 1990s. How do you weigh something that's invisible, 27,000 light-years away, and hidden behind a thick fog of interstellar dust? The answer is gravity. An invisible object still has mass, and mass still pulls on things. It's like finding a magnet buried in sand. You can't see the magnet, but you can see its location by how it pulls on iron filings you sprinkle on top. For Sagittarius A star, the iron filings were stars. The theory was simple. If a supermassive object was hiding at the center, then any stars nearby should be orbiting it at insane speeds, like planets whipping around the sun. All astronomers had to do was track them. Of course, all they had to do was a ridiculously difficult task. The galactic center is a chaotic swarm of stars. From Earth, it's hidden by huge clouds of gas and dust that block most visible light. On top of that, our atmosphere blurs everything. Looking at the stars from the ground is like looking up from the bottom of a swimming pool. The turbulence makes them twinkle, which is great for poetry, but a total nightmare for precision astronomy. It was impossible to track individual stars so far away. This is where two rival teams, one in Germany led by Reinhard Genzel and one in the US led by Andrea Ghez, would pioneer a game-changing technology. Genzel's team used the European Southern Observatory in Chile, while Gez's team used the giant Keck Observatory in Hawaii. Both were in a race to get a clear view of the galactic center. Their secret weapon was called adaptive optics. Here's how it works. The telescope shoots a powerful laser into the sky, creating a glowing artificial star high in the atmosphere. A camera watches how the atmosphere makes this fake star twinkle. A computer then analyzes that twinkle thousands of times a second and sends commands to a flexible mirror in the telescope's light path. This mirror deforms itself in real time, canceling out the atmospheric blur. The result? An image almost as sharp as if the telescope were in space. With this new superpower, Genzel and Ghez could finally cut through the haze and see individual stars at the heart of the Milky Way. Starting in the mid-1990s, they began their work, taking picture after picture, year after year, plotting the positions of the stars closest to Sagittarius A star. One star, in particular, became the hero of the story. Genzel's team called it S2. Gez's team called it S02. Over the years, as they plotted its position, the data points formed a clear path. The star was moving, and it was moving fast. It was undeniably orbiting an invisible point in space, the exact point where the radio signal from Sagittarius A star was coming from. The big payoff came in 2002. They watched S2 complete a full 16-year orbit. As it swung in close to Sagittarius A star, it accelerated to a mind-boggling 5,000 kilometers per second, or 11 million miles per hour. That's over 1% the speed of light. To give you some perspective, at that speed, you could circle the entire Earth in less than 8 seconds. This was the data they needed. Using the star's orbit and its speed, the teams could use Kepler's laws of motion, the very same laws we use to weigh our sun. The math was undeniable. For S2 to move that fast on that path, it had to be orbiting something with the mass of roughly 4 million suns. And all that mass was packed into a tiny space. S2's orbit proved that all 4 million solar masses were crammed into an area no larger than our solar system. This was the killing blow for other theories. A cluster of millions of stars would be much bigger. A swarm of neutron stars would be unstable and fling itself apart. The only thing that could be that massive and that compact was a supermassive black hole. In 2008, Genzel's team published their findings, calling it the best empirical evidence that supermassive black holes do really exist. But the story wasn't over. S2's orbit offered an even bigger test. Einstein's theory of general relativity says gravity isn't a force, but a curve in spacetime. Near a supermassive black hole, those effects should be obvious. Two predictions were on the line. First, gravitational redshift. As light climbs out of a gravity well, it should lose energy, and its wavelength should get stretched toward the red end of the spectrum. Second, Schwarzschild precession. The star's entire elliptical orbit should slowly rotate, creating a rosette pattern over time, instead of a simple repeating oval. S2's next close approach was due in May 2018. This time, astronomers were ready with an even more powerful tool: gravity, an instrument that combined the light from 4 massive telescopes into one. As S2 whipped around Sagittarius A star, hitting nearly 3% the speed of light, gravity measured its light with unbelievable precision. The results were perfect. They saw a clear gravitational redshift, exactly as Einstein predicted. A couple of years later, they confirmed the precession too. S2's orbit was rotating forward, just as general relativity demanded. This was it. Decades of patient work had paid off. Genzel's and Gez's teams had not only weighed the invisible monster, they had tested the fabric of space-time around it and proved Einstein was right. For their monumental work, Reinhard Genzel and Andrea Ghez were jointly awarded the 2020 Nobel Prize in Physics. They had found the ghost. They had weighed it. They had proven what it was. But one last, seemingly impossible challenge remained. Could we actually take a picture of it? How do you take a picture of something that by definition eats light? Well, you don't. The black hole itself is the blackest black imaginable, but you can photograph its silhouette. Einstein's theories predict that a black hole's gravity will bend the light from the glowing, superheated gas swirling around it into a ring. This ring of plasma should frame a dark central region, a shadow, which is the event horizon itself. Capturing an image of this shadow would be the first direct visual proof of a black hole. The problem was the scale. Sagittarius A star is 27,000 light-years away. Its shadow is only about 27 million miles across. Trying to see that from Earth is like trying to photograph a donut on the surface of the moon. No single telescope could ever do it. You would need a telescope the size of the Earth. So that's exactly what a global collaboration of scientists decided to build. They called it the Event Horizon Telescope, or EHT. The EHT isn't one instrument, but a worldwide network of radio observatories, all synchronized by atomic clocks, from Chile to Spain, from Hawaii to the South Pole. These individual dishes all stared at the same point in the sky at the same time. By combining their data, they could act as a single, planet-sized virtual telescope. It's a technical and logistical miracle. In April 2017, the EHT network stared at the heart of the Milky Way for several nights. They collected a staggering amount of data, petabytes of it. So much, it couldn't be sent over the internet. Instead, thousands of hard drives had to be physically flown from all over the world to processing centers in Germany and the US. The drives from the South Pole couldn't even be shipped until the Antarctic winter was over. Then came years of painstaking work. Imaging Sagittarius A star was way harder than the EHT's first target, the black hole in galaxy M87. That black hole is a beast, over 1,500 times more massive than ours. The gas around it takes weeks to complete an orbit, so it sits still for its photo. But the gas around our black hole whips around in a matter of minutes. This means our target was constantly changing and flickering. As one EHT scientist put it, it was like trying to take a picture of a toddler who can't stay standing still. On top of that, we have to look through 27,000 light-years of our own galaxy's dust, which scatters the radio waves and blurs the image, like looking through frosted glass. The team had to invent new algorithms to unscramble the data and account for the constant flickering. It took 5 years. Finally, on May 12, 2022, the Event Horizon Telescope collaboration held press conferences around the world. There it was. For the first time in history, humanity could see the shadow of the supermassive black hole at the center of our own galaxy. It was a fuzzy, beautiful ring of light surrounding a dark central void. That ring is the glow of superheated gas, its light bent by extreme gravity. And the dark patch in the middle is the black hole's shadow, the event horizon, the point of no return. The ghost scientists had chased for 50 years was finally on camera. What was amazing was just how perfectly the image matched the predictions. The size of the shadow was a direct test of general relativity, and it passed with flying colors. The mass of 4.3 million suns, which Gez and Genzel had calculated by watching a single star, was visually confirmed by the size of this shadow. Two completely different methods, decades apart, had arrived at the exact same answer. It was a triumph. The long hunt was over. From a faint hiss in a field in New Jersey to a breathtaking image of a cosmic monster, the 50-year journey to reveal Sagittarius A star is one of the greatest scientific detective stories of our time. It's a story of human curiosity, generational persistence, and global collaboration. We chased a ghost through a fog of cosmic dust, and we finally found it. This image is more than just a picture. It's a confirmation. It tells us that Einstein's theory of gravity works even in one of the universe's most extreme places. It tells us that the object governing our galaxy is, without a doubt, a black hole. But like all great discoveries, this one opens up more questions than it answers. Why is our black hole so quiet? Compared to other galaxies, where black holes blast out huge jets of energy, ours is a gentle giant. What does that say about the history of the Milky Way? The image also gives us clues about the magnetic fields that control how gas falls into the black hole, a key part of the puzzle. The quest is far from over. The Event Horizon Telescope is already being upgraded. With more telescopes and new technology, the next generation EHT hopes to sharpen the image and eventually create a movie. Scientists want to see real-time videos of gas swirling around the event horizon, to watch matter take its final plunge, and to see this extreme environment unfold right before our eyes. We have met the monster at the heart of our galaxy. Now, the real work of understanding it begins. And it's a powerful reminder that we live in a universe full of wonders, waiting just beyond the edge of what we can see, daring us to look into the dark. If you made it this far, you're clearly as passionate about these cosmic stories as we are. Thank you for joining us on this 50-year journey. There are so many other mysteries out there waiting to be explored. Let us know in the comments what grand discovery you'd like us to tackle next. And for another deep dive into a black hole, be sure to check out our video on M87 right here. Until next time, keep looking up.